And today we are on chapter 2 of our little journey, and I will be showing you SIMIT. So without further ado, what is SIMIT, I guess, is the place to start. Before it, historically, when we showed SIMIT, we used to focus on SIMIT being the gateway for our simulation packages to be able to interconnect, to talk to each other, and that's all we did. And I think we didn't do justice. So this is why I decided to show you SIMIT standalone really today. But then if you are interested in this integration, in the value added, please, stay tuned and come join us on Thursday, where Anubi will be showing you the entire story. So to address the question of what is SIMIT, well, let's just SIMIT. No, not this SIMIT. Siemens maybe. So if you look for Siemens stuff in general, you will normally find two places with some information: the Siemens.com and the support industry. And while Siemens.com is a good place to find, yes, to find some information, this will mostly be sales-related information. So we can see here that SIMIT is a simulation platform that enables comprehensive tests of automation application and provides the realistic training environment for one actually finds any other software that we probably make. I would always advise going to the support.industry.siemens.com and either using the search engine or using Google to get here. And this place here is probably the best place for finding information about SIMIT. So the overview of SIMIT simulation platform. This includes all the links for downloads, for manuals, FAQs, application examples, and the great thing that is the media system. And if the information that I give you today might not be enough for you, or you just simply want to learn more, maybe learn about creating these connections even before a newbie shows it to you on Thursday, you can always go here and you will find loads of videos, loads of information how to do stuff. If you, for example, go to use cases, couplings, you will find information how to create your couplings, what SIMIT can talk to. So this actually covers maybe the things that I'm not going to be covering today, as we just don't have enough time. And as I said, I just want to show you SIMIT in its full grace. So again, SIMIT is a simulation platform that allows you to simulate the external components. And I actually have one slide. I'm not going to present you a slide deck today. I just have a single slide for you. And that's this slide. So you normally start with SIMIT where you already have your PLC code or part of the PLC code, and you'd like to then test it. So either it's a PLC code that you will be testing with PLC Sim, PLC Sim Advanced, or maybe you even have a real controller, because this is possible with SIMIT as well. So you have some code, you'd like to test it. But this code depends on signals from maybe external sensors, external drives, peripheries, or maybe it actually reads information from entire technological lines, be it some processes, maybe some external systems. So you are depending on this information in a PLC simulation, and there will be no way for the simulation to actually progress without getting the data. And this is where SIMIT comes into play. It allows you to simulate all of them. So okay, that's it. No more slides. Let's just fire up SIMIT. Actually, I already did it a second ago to make sure it works. Because SIMIT, if you look at the licensing model of SIMIT, it requires a dongle. And the dongle needs to be plugged in constantly. So yeah, you need to make sure that the dongle is passed to your VM if you are running it in VMware. So that's SIMIT for you. What we're going to do first, we're going to create a new project. Now, let me create quickly a new folder. Today is 5th of the 5th. Very nice. The project, I'm going to give it a great name of Project 1. There you go. Project View. That's the SIMIT interface for you. I'll quickly run through the things that we have here, and then I'll just show you what SIMIT is, how we can use SIMIT, and maybe talk about some use cases while I'm doing that. So on the left-hand side, just like in TIA, for example, you have your project tree. And here, one of the very first things that you can and would normally do are the couplings. So the couplings are the interconnections between some external packages, external data sources into your SIMIT. And this is exactly the thing that I'm not going to be talking about today. But just to go through the couplings, as you can see, we have things like PLC SIM Advanced, PLC SIMIT, Virtual Controller for 400s, OPC Way, MCD, and so on. And you could even create your own couplings. And this is what allows SIMIT to exchange the signals between external packages, like your simulation running in PLC SIM Advanced itself, and maybe then another external packages. So these are the couplings that I'm not going to be touching. The next thing on the left-hand side are the charts. And the charts are where all the magic happens. Normally, you'd probably give it some meaningful name, but me, yeah, unfortunately, I left it as chart. So that's your whiteboard, your drawing board, where you would be creating your program, creating your simulation, and bringing your digital twin to life if you wish. To use this, on the right-hand side, you have pretty much like in TIA, you have your components, so your libraries of different things that you can use. The components are like predefined blocks of code that we can just drag and drop. Then we have controls for manual control, macros, graphics, templates. There's a lot of different things that you can do in SIMIT. But okay, let's just make up a problem that we could probably address with SIMIT. Or maybe not. Let's just think about the problem. I have a PLC code now that I'm testing with PLC SIM Advanced. If you joined us yesterday, you probably know exactly what PLC SIM Advanced is and what it can do. If you haven't, I would strongly encourage you to watch the recording of next webinar. I think it was great. But we have the simulation running in PLC SIM Advanced. Great. Our code goes through, then we hit a network where we're actually waiting for some feedback. Well then, do we force this bit to be high? Do we include some extra function blocks to provide this feedback? None of these solutions are really great. I mean, the third thing we could do, we could probably wait for our real system to be built and then evaluate it. But this is just wasting time. This isn't the way of lean development. And this is where SIMIT can come into play. And it can be helpful even in these simple scenarios where we maybe just want, some feedback. So if we switch a device on after, let's say, 10, 15 seconds, whatever, it gives us a feedback that allows us to evaluate whether everything worked fine. So how would we address this very, very simple issue in SIMIT? Normally, if we had our couplings defined and we're using external signals, we will simply go to components, to connectors, grab ourselves an output, which would be our output from, for example, PLC SIM Advanced, so your PLC code, and then an input, which would be an input going back to PLC SIM. So these could be, like physical DI and DQ. And then for feedback, depending on your requirements, you could either include some logic in between them, or maybe, a simple delay might suffice as well. As I said before, I will be focusing on SIMIT today. So no signals, no external signals at least. I will just be using manual controls. So instead of my output from the PLC, I will just have a switch so I can manually adjust the signal. And then to see what's going on, I will have a binary display. Then, as I said, I could use either some logic in between them or maybe, something like a simple delay. So if I go to binary extended functions, I can find a delay function. It might just do what I need for this specific purpose. So if I drag and drop my delay, maybe space them a bit, I can then interconnect my signals. Maybe let me make it slightly bigger for you. Interconnect my signals. You know what? Actually, there you go. Looks slightly better. Now, as you can see, we have two parameters. If these weren't obvious, although TON and TOFF are kind of obvious, I could always click this, press F1, and find more information about what they do. The manual for SIMIT, just like the manual for TIA, is really, really good and does explain all the parameters that are included in your different components. So we have our input/output, out to slash input, depending on how you actually see these things. And then we have our delay. So for our delay, we actually can either, change the time for the on delay from an external source, or, and this is what I'm going to do in this case, we can just punch in a number. So for me, a delay of 5 seconds. So if my PLC code switches a device on, I expect this device on to be on after 5 seconds and to provide the signal back to my PLC code. Let's test it quickly. Yeah, I'm going to save the chart. I guess I should save the project. I never had, this good habit of saving the project. I guess I should be doing this way more often. So there we have our code. Let's switch this on. Let's wait 5 seconds. There you go, switched on. So a very simple feedback loop done just like that. And to be perfectly honest with you, this is probably way too easy example for SIMIT, although we did have few customers who wanted to do exactly this. So they wanted a full control over their external simulation. They wanted to detach it completely from their PLC code and said this is all they need. They just need to turn something on and have a feedback from the system saying it turned on. That's it. So you could do it for this purpose. Now, since we have time, I guess it's a good moment to introduce the, let's say time compression in SIMIT. So 5 seconds maybe isn't exactly a lot, but sometimes it can certainly feel like a lot. And if this was set to 60 seconds, maybe I don't necessarily want to wait 60 seconds to see if something actually happens. So what I can do, I can change this setting. And rather than, the time slice being at 100%, I can speed all the operations, the time-based operations, at 5 times. So if I switch it to fast, turn it on, it should turn on much quicker. Then the same if I go to slow. So maybe you have a very fast process. Maybe you have some drives ramping up very quickly, and you'd like to monitor what's going on with them. You could actually turn it to slow. So you slow down the event 4 times. So we set it to slow, and then we wait forever for this input to switch on. It's not forever, it's 20 seconds. It just feels forever when I'm talking and watching the input go high. No, I can't do this anymore, I'm sorry. But believe me, it would go on after around 20 seconds. So we just made ourselves a little feedback loop. And when talking about feedbacks, you can't really not immediately think about safety. And again, if you joined us yesterday, you probably know now that, PLC Sim Advanced can simulate your safety program for you as well, which is great, which is handy. But then again, your safety code will be expecting some feedback from devices. And it's even worse than with normal devices, because it would probably be quite often expecting signals like your QBAD, like your VSS, to make sure that everything works fine. Your modules will quite often be something like, 1 out of 2 evaluation, where you will have 2 signals coming from one sensor into your module, and this will be then evaluated depending on the settings of your digital input card, for example, and then a correct signal will be provided to your code in TIA and evaluated by this code. But then again, it will start looking at VSS or QBAD probably in most of the cases, or at least quite often. So how would we approach a problem like this? Again, we could easily do with SIMIT what you could do theoretically. Now I have, one input here. I could make get another one, so I would have 2 inputs. Then put some logic here that evaluates and makes the output go high if both inputs are high. And then depending on what happened here, it would switch my VSS bit. Then I could probably include something to evaluate whether reinitialization is required, so like a reset bit for my module. Then when this was done, I could make this a template. So templates are like few blocks put together that you can simply reuse. So I could make a template of it and reuse this template whenever I have a fail-safe input. Now this sounds like a lot of work. It's not terrible, but it just seems boring, copying things over. So what if I had 16 input card, I would need to copy it 16 times. Well, it's not end of the world, but nah, that's wrong. Let's see if there is something that can help us. So remember I mentioned the best place for SIMIT as support.industry.siemens.com. Let me even punch it for you. Support.industry.siemens.com. I hope it takes you to the English page. Yeah, perfect. So I said I'd like to simulate safety. SIMIT, simulate safety modules. Let's see. There you go. The first thing is an application example. SIMIT components for the simulation of fail-safe modules of the S7-1500. Just what I needed. And there you go. There's a description saying that what we can find here are the blocks for FDIs, FDQs, FPME, so your fail-safe power module of the ED200SP. So yeah, this should be exactly what we need. We can download the documentation. If you go into the documentation, you will find information about what actually is supported, what it does, what the different settings mean, and so on and so on. And don't worry, I won't be reading this for you. You can all read it if you feel like it later on. All this is free for you. The only requirement is you need to register to our support page. If you haven't done so already, I would strongly encourage you to do so. There's loads of free stuff that you can grab from here. And as my colleague said, in the past, just steal with pride. If someone did it before, just reuse this if you can. And no, of course, if the license allows you to reuse it. So let me log in. Oh, and I do hope I remember my password. There you are. Yes, download it. That's down. Okay. So we just downloaded our SIMIT library for F components. Let me extract it. Let's just see what's there. Well, I hate being in downloads because it's really hard to navigate to downloads from other systems. So I just put it on desktop. So there we go. What we find inside, we have 5 blocks. Now these blocks / files have an interesting CMP extension. And what these are, they are SIMIT or simulation components. So they are not really SIMIT project files, they're just simulation components. And they have CTE icon. And let me try to open one of them and let's see what's inside. So as you can see, this file is another piece of software that's called SIMIT CTE. It stands for Component Editor, or at least I believe it stands for Component Editor. So you remember these components on the right-hand side in SIMIT. SIMIT CTE allows you to create these. So rather than building everything from these, simple blocks, components that already exist, you can actually start making your own components. And this is what my colleagues from our headquarters did when they prepared this little library. So you could do a library like this yourself. If you're doing something all over again, quite often reusing the same things, you could use SIMIT CTE to build your library of objects that just do their job for you and are maybe containerized in one simple block. And if we go through this, see, this is a great thing. And I imagine that some of you might have spotted already. These blocks are not know-how protected, which means that you can download the blocks from the library, from our website, open them in CTE and do whatever you want with them. Again, still with pride, you want to reuse them. Maybe some modules that you are using are not actually here in this library. Why not just take the code, adjust it, and make it work for your specific use case? So if you go through this, we can see we have 9 input connectors. We have 16, that's a guess. Yeah, it would make sense. We have 16 outputs. So we are evaluating 8 signals. We are evaluating the reset signal, and then we are outputting 8 signals for our safety in the PLC and 8 DS signals. And all these signals are what a real digital input, a fail-safe digital input card would normally provide you with for your code. Then if we go into parameters, we can see that our channels can be set to different type of evaluation, just like your real card would normally allow you to. And then if we go to cyclic calculations, we can see what is actually being done. So the program isn't very complex. It just evaluates the Boolean states of different inputs, and depending on them, it sets the outputs, it sets the VSSs, it might require passivation. It's actually not doing just this, it's calling for two different functions. There is an evaluate function, which takes these inputs as parameters, and then there is value state function that takes these ones. And these functions can be actually seen here. So you can see exactly what this thing does, and you can modify it to your liking. Then we have the visualization bit of SIMIT CTE. So if you go here to basic symbol, we can actually start defining how the symbol is going to look like in SIMIT. So this one is quite simple, and I mean, what else would you possibly want? We have 8 inputs where you would normally connect your signals from, let's say, your guard doors. Then we have 8 outputs, 8 VSs, which then go to your PLC code, to your blocks in your failsafe program, and then we have the PV reset for your reintegration. So what would you possibly want? Well, maybe I would like to be able to simulate these inputs going high manually. All I would need to do is drag some switches here, interconnect them in my code, and off I go. I have, made for my use case block that does exactly what I need, and maybe instead of me having to connect signals, it has switches. And this is just an example, because you can make these blocks anything you'd like. You can make your very own custom blocks that will simulate the craziest things. And the great thing with the newest releases of SIMIT is that you could actually build your simulated component in something like AimSim, like MATLAB Simulink, and then create an FMU file, import this file into SIMIT CTE, and embed this simulation that you prepared in AimSim or in MATLAB into your SIMIT simulation, which is a great thing for more complex scenarios or more complex control objects. So let's close the CTE for now. No changes. And let's go back to our SIMIT. So we download these components. Let's just grab them now. Desktop, safety, nothing here. But when I click open, it's actually going to scan the entire folder and grab all the components for me. So if you open this up, we can see that all the components are now available. So let's say I'd like to simulate, let's say that, in my PLC code, I'm using an 8-channel FDI card. There you go. Maybe now it's slightly too big for us. Let's put it here. So you have an 8-channel FDI card that, just as a normal card, can work in either 1 out of 1 mode for the channels, or at 1 out of 2 modes. So let's quickly test it. So we have these switches. Let me copy them over. So I will be using 0 and 4 because these channels are connected together. So if I switch 1 out of 1 evaluation to 1 out of 2 evaluation, they will work together. And then the third signal for me will be my PV reset. I'm terrible at placing things. And this is why I love this little feature. And distribute evenly. Yeah, there you go. 0, 4, PV reset. Great. Now let me grab some of these indicators. What do I need? I need 0, I need 4, I need 0, and I need 4 for VS. And this should give me spacing. There you go. I'm ready for manual simulation of my FDI. Again, this maybe isn't how you'd normally work with SIMIT, because normally, rather than having manual controls here, you would have your signals from your couplings, or you could do both. So you could have this coming from your signal, or you just include an OR here, or coming from your manual control. So if you don't want to test something in the PLC, you can always press things here manually to overwrite some settings. So let's start our simulation and see what happens. So because this is by default set to 1 out of 1, I would expect the in0 and in4 to work independently. Let's put this back here. But first, I need to reintegrate my card. VSs are high, which means the card is working okay. Everything works as expected. So there is no signal on in 0, so there is no output on in 0. So if we turn this high, there you go, high, turn this high, exactly as you would like it to work. And then if we stop the simulation, go into the card, just like you would probably in the properties in your TIA program, then go here. We change the settings for channel 4 to be one of the 2 equivalent, which means that if both input signals are high, our output on in 0 will be high. In 4 will not be reacting to changes, and VS4 will constantly be set to false. There you go, we reintegrate the card, VS4 set to false, VS0 set to true, so everything is as it should. Then set this high, nothing happens, this high, nothing happens. If we set both high, in 0 is now high. And there you go, perfect simulation of your fail-safe digital input card for S7-1500 simulation with PL System Advanced, because these signals can then be interconnected very easily with your fail-safe code in PLC Sim Advanced. So we simulated turning something on and getting a feedback. We simulated our fail-safe module. So let's say we actually simulated a safety guard door. Now I guess the question would be what these guard doors should or could be guarding us from. One of the things that maybe is a bit dangerous and would require, switching the process off in fail-safe mode would be the vicinity of steam. Steam isn't exactly very good for human skin or any other part of a human, to be honest. So let's think. How could we simulate the process of creating steam? Now, the thing that I didn't mention and normally mention it at the very beginning is SIMIT isn't SIMIT 10, and we just start talking about SIMIT in factory automation environment. So what about previous SIMIT versions? Well, SIMIT was here with us for a very long time, but it was always a toy of process industries. They were using it very heavily for simulating their processes, for simulating, the chemical processes, tanks, pipelines, you name it. So if you just want to simulate some pumps, some tanks getting filled, SIMIT has the components for you. Now this chart, because I want it big, let's just leave it like this. Let's create another chart. And yeah, this one's going to be called chart 1. So let's quickly think about how we would maybe create the simulation of steam production. We have these libraries here on the right-hand side that we could use. One of them is FlowNet, and this is specific for water and steam, really, but also does generic gas or liquid. So we can start by adding ourselves a P node, which will be our pressure. So if you think about the system, first we have our line supply, which will be supplying our factory with some pressure. Then let's drop a valve here so that we can say, do we want it open or not? Then we can grab a storage tank for the water that we get from the supply. Then I would say probably another valve. We could use with 2 stubs instead of 1, so the water can actually go somewhere. There you go, the water going to the next valve. Now the pressure will probably not be enough for what we need, so maybe we could use a pump. Then after this pump, well, if I want steam, I could do with some heat, so I'm going to add an electric heater. So electric heater, at the output I would now expect some steam. So let's actually now, rather than adding storage tank, because if you press F1 on storage tank, you can see that this is an open water tank, so not very useful for steam. We will be much better off with a drum. So this now goes to, I think this one is the one that we want. Yeah, this one goes to our drum, and then our drum will have a valve. Go here. So we have a valve, and then we will have, let's say, our nozzle to distribute the steam. Let's say our steam is actually used maybe in a beer plant, so we have a beer plant, we have some bottles, and these bottles need to be cleaned with steam. So we will have now an M node, which will be consuming our steam for us, Now, all we need is to add some manual controls for these objects. So manual control for my valve, for my other valve, for my pump, for my electric heater, and for my last valve. I'm going to connect them quickly. Okay, let's adjust the settings as well. Where are we? There you go. So the pressure that we'll be getting from the system, let's say 2 bar. Now, what do we want the tank to be? If we go here, we can say, is there anything already in the tank or not? Our tank is going to be empty. The pressure outside the tank is 1 bar, and we leave all the other unchanged. But I wanted the tank to be big, and I mean big. So 10 cubic meters. No, it isn't big. I want it to be at least 100 cubic meters, so 100 tons of water at 5 meters of height. Now let's make it a high one. There you go. That's good. Now we will be producing steam. So I want high pressure steam in this container. So my pump, let's say nominal pressure of 25 bar, zero flow head on 30 bar, and nominal mass flow for 25 kilograms per second, 50. These obviously would be the numbers that you get from someone who put the system together, who know what they are doing. Me now, I'm just playing with the numbers to get, well, a quickly working simulation rather than a normally working one, because I just want to show you how these things can be easily manipulated, how these things simulate anything that you might possibly want to do. Next thing is our electrical heater. And as you can see, by default, it consists of 4 tubes that weigh 10 tons each. I want 10 tubes, so 100 tons of steel is enough for me. This should get me a really nice heating. Then this slider goes 0 to 100, and this slider will be controlling the power of my electrical heater. And I said I want it quick, didn't I? So let's make it quick. So I will now be able to adjust the slider 0 to 50,000, which will get me a really fast temperature rise on the electric heater, on the tubes themselves, which will allow me to just quickly demo this for you. Then we have our drum, and I guess it would make perfect sense for the drum to be empty, because we don't want our steam container to be half full of water at 20 degrees, do we? So 0 here, 20 degrees, yeah. So this is the temperature of the tank itself. Now if you start pumping the steam, and if the steam is, let's say, around 100 degrees, it will probably cool down quickly in the tank and turn into water. I don't want it, so I just be on the safe side. Let's make it a bit warmer. Okay, then we have our last valve that regulates the flow to our output. This one is 0 to 100, and the output itself, mass flow of, I have no idea what the consumption of something like this could be. Let's say it will be consuming 2 kilograms per second. So this all should be good now, unless my interconnect is something wrong. Let's say what happens. Nice. Okay. So let's fire this up. So we have 2 bars in the input, but our valve is closed. You know what? There's one more thing that we can do. We'll make it look slightly better and better for diagnostics. There you go. Show flow, yes. Show flow direction, yes. I want this setting. Oh, no. I want this setting to be true for all my valves. So I will know exactly, if the water is flowing or not, and I should have the same thing available here. So let's save the project first, and let's see. Okay, so again, we have 2 bars here, nothing else happening. Let me bring up the valve, nothing flowing through the valve. Let me open the valve at 10%. As you can see, the water is now slowly flowing. Nearly 10 kilograms per second of water flowing into my first tank. Tank is now very slowly flowing with, filling with water, sorry. Okay, 10%, I'm bored with this, 100%. Okay, so we are slowly getting the water into our tank. That's perfect. Then we have our electric heater. The heater is currently at 23 degrees, so let's make it heat very quickly. There you go, the temperature rising. I'm an impatient man. Fast mode is what I like. Okay, 100 degrees, that's fine. I guess we can lower this down now. Still keep it high. So as you can see, the temperature is now rising slowly. There is no water flowing through this currently. So, well, you would probably normally avoid going into very high temperatures if there is no water flowing. Now, if we open the tank is nearly empty. There is nearly no pressure, and the pressure in this storage tank on the left is higher than the storage tank on the right. So even without the pump, if I just open the valve fully, I should get some water flow. And as you can see, the water flow is immediately causing the temperature in my first tube to drop. But because I have 10 tubes, the last tube is still gaining temperature. So this is slowly filling with water now. And if I wanted to start filling with water faster, I could maybe use my my pump. So we are currently pumping 8 grams per second. This is slowly going down while the temperature, the pressure in the chamber here increases. Let's crank it up a bit. Pressure difference is building up. The flow is now 40 grams per second, which caused a significant drop on the first tube, but the last tube is still gaining. So we now have nearly 5 bars in our container here. And if I wanted, I could now simply start using my steam. Sorry. There you go. 2 grams per second of consumption, and we should see, this now is increasing slower. If I close the valve, I will see that we are now losing the steam from the cylinder. So quite a neat simulation with quite a lot of complex mathematical equations included here, and all this simulated in 10 minutes. Now think about, normally you would need to probably have all of this done manually somehow. So I said that this is for cleaning beer bottles, didn't I? So where are the beer bottles? What we can simulate now, we could actually simulate a conveyor system as well. Let's bring another chart. So we have a chart now. Go back to components, and now we have another library called contact library. And this library is all your different conveyors, and you can build, normal conveyor systems, or you could even build, like a rail-based system with carts on it. So let's just add a conveyor. Let's say that this conveyor brings the bottles in. Then we have another conveyor, and this is where the bottles get cleaned. Another conveyor, let's say we here evaluate if the bottle is clean or not. If the bottle is clean, that's fine. Just go directly here. But if the bottle isn't clean, what I want to do is I want it to go back. Sorry, I need this. So I want it to go here. Yeah. Let's move it to the right. Oh, too much. Just this one. Yeah, there you go. It's quick, isn't it? I do love the contact library. Make this longer. I can make it longer from the other side, I think. Or I could just rotate it as well. Oh, come on. There you are. And the question is, are they connected here? Not very good at drag and dropping today, am I? There you go, should be fine. But we need something on it, don't we? So the thing that can go, well, it's basically anything, but we have these materials here, and you can find some boxes here. Yeah, I know I said bottles, and these are boxes. So I guess what you could do if you wanted, we could do a SIMIT CTE, and rather than using the boxes, because you can like the boxes for whatever reason, although I guess the bottles could be in the boxes, couldn't they? But still, if you wanted the bottles to look like bottles, you could go in SIMIT CTE, create a new component, call it bottle, I'll put it here, create, just go basic symbol, polyline, terrible at drawing things, I'm sorry. Does it look like a bottle? I hope it does. Yeah, forgive me. It is kind of a bottle, isn't it? You know, like it's not terrible bottle. It doesn't look like a bottle. Okay. Anyway, save it. That's what you're gonna get. So again, open the user components, documents, CTE, open up. Yeah, there's my bottle. Okay, so I have a bottle. I don't want one bottle. I want multiple bottles. So you have these lists. Lists are quite cool. So I can take my bottle, hold Alt, drag it here, and say, yeah, give me 10 bottles. There you go, bottles with different sizes. Now, these sizes, let's see how it looks like. I guess that we could use a different scale. So this slightly different size. Then here is where the bottles are going to start spawning. So we are using material type bottle. This is the name. Material list. I want to have initially 5 bottles spaced every 20. Let's save it. Let's see what happens. Where are my bottles? Oh, okay. Well, but yeah, you have 5 bottles, don't we? The conveyor isn't moving because the conveyor needs speed. And like every bit that I have here will need some speed. And this normally would be controlled by your PLC code. I will show you how just in a second, but I will need to be doing this manually for the time being. So I have these speeds. So let's start the first conveyor. As you can see, there are sensors in the conveyors. You can place additional sensors, and you can read these signals into your PLC as well to evaluate what's going on and to make sure you know that you get exactly the same signals as you would get from a real conveyor system. So let's start moving this slowly. Yeah, there you go. This is stopped now. Oh, each other 5. This is cleaning, so maybe on the cleaning station it should. Oh, not 520. It should be going slower. So when it goes here, let's say normally evaluate whether the bottles are clean or are dirty or not. And it goes into this turntable. On the turntable, it will rotate. It will move slowly. And if our bottles are clean, that's fine. Maybe it can actually go a bit faster. Let's go there. In the meantime, let me just adjust these speeds. I could set them, like preset them, but I didn't. So all these bottles now happily go where they should be going. Yeah, these arrows need to all make sense. And this one needs to go there. So all these bottles, let's pretend they are clean, okay? They're all good bottles. They can move along. But let's say now we dump ourselves a worse bottle that needs to be cleaned with steam twice. So we take object ID 1 from our list and we just create a bottle. Again, this can be done directly from your PLC simulation where you can just interconnect these signals. So the bottle is now getting cleaned with the steam that we just did. If anyone were to enter here, then we would maybe use the code from chart 1 to trigger a safety response. And as soon as the bottle gets here, quick, we say, oh, this is a dirty bottle. So yeah, we just control the turntable. This is exactly how you can simulate your conveyors without the conveyors, being built. So you can start way ahead of the curve and start before anything else is ready for you. Now I said that this can be controlled from the PLC sim or PLC sim advanced, any of these. Just to show you quickly, there are these templates. And if you open the templates, you have different templates for different conveyors. And they actually have these blocks, which are all already ready for interconnection. So they are all just waiting for a coupling name to be able to be controlled from your PLC instance. And this is how you would write your simulation. So with SIMIT, you can easily simulate, well, anything you'd like, really. But what I showed you today is simple feedback loops, simple safety systems, process, so steam preparation, and conveyors simulate as well in 40 minutes. It will probably take me longer to figure out the controls on the conveyors and how the PLC code needs to be structured. So having this as a help to guide me now and for me to be able to quickly test snippets of my code, I think it's invaluable. But yeah, that's everything that I wanted to show you today. And if you are keen to know more about how to integrate these things together with PLC Sim Advanced, maybe different packages, maybe you actually do need proper physics as well, please stay tuned. And maybe we'll be talking about MCD, which can simulate all the physics of a machine as well for you tomorrow. And on Thursday, there will be a session that will be showing this integration, PLC Sim Advanced, SIMIT, MCD, all working together. So yeah, if you have any questions, I'm ready now. We have 8 minutes left, so fire away.
Michael, thank you very much for sharing. To kickstart the questions, I actually have a question from someone asked yesterday. Nick showed PLC Sim Advanced, and he showed the free application example of CEOS with regards to crosslink for interconnecting of signals. And in the crosslink example, it shows it can simulate a V90 drive with Telegram 3. And someone was asking about how could they simulate other telegrams. I was thinking, obviously, you could show perhaps here in SIMIT the drive telegrams, and maybe that's how you then connect to your conveyor system.
So I'm currently running SIMIT 10. On SIMIT 10.1, you have even more. On SIMIT 10, we have Telegram, Profit Drive Telegram 1 and 2, and you can use these to build your proper telegrams from like bits. But in SIMIT 10.1, which is already released, I've just fired up the wrong VM, it would seem. You also get Telegram 111, for example, for EPOS and the 900 telegrams. But if you want even more, all you need to do is, again, support side and SIMIT. Drives, I do hope I find something. Drives behavior library for SIMIT. And then, all these people tell me it's hard to find things on the support side. No, it isn't. You type SIMIT, you type drives. There you go. There are your telegrams. And again, you have a SIMIT project, you have a SIMIT library, you can just download them, and you will have your ready-made components for telegrams 81, 82, 80, what are these? Well, for all different telegrams, anything that you might like, telegrams that I never heard of, and I do know drives, so.
That's perfect, and that could obviously be used like in connecting to your conveyor system. In addition to that, Michael, on that conveyor system, I guess if we had some bottles moving down it, and linking back to what I spoke of in the intro, where we got the RFID tech talks already available to watch in the back catalogue at the website. RFID in SIMIT, if we wanted to track and trace those bottles moving down your little conveyor there, would that be something we could achieve here?
Certainly, and I could probably go to SIMIT and type SIOS and type SIMIT RFID for you, but you can do it yourself if you want, and you will find that it is perfectly possible to use RFID technology within SIMIT, and it is actually amazing because what you can do, you can not only simulate the simple signals going through, SIMIT can actually help you simulate all the information being read and being written. So if you now imagine our bottles and boxes full of bottles, each of these boxes could have a simulated RFID tag attached to this. Then on the conveyor, you would have simulated RFID readers. It goes to our first station, it reads the state, it knows these bottles are bottles, of an X substance, let's say, and it needs one cleaning cycle. Okay, so then the information is read, and we do one cleaning cycle. But then maybe some bottles need 2 cleaning cycles. So we, again, read this information, go through first cleaning cycle, save the information saying, okay, these bottles went through first cleaning cycle, go to the turntable, go back to cleaning, clean again, say cleaning completed, go out and be refilled with delicious drinks.
Brilliant. Any further questions? Yep,
hello.
go ahead.
As Niall Mitchell, PSE. What was the name of the tool that you used for the creating the bottle or the list or the graphic for the bottle?
This was SIMIT CTE. So this was the component editor that I showed you when I first downloaded the library for the safety objects. So I used SIMIT CTE for something very, very, very basic with the bottle creation. So I created a component that does absolutely nothing. It just looks like an ugly bottle. But normally you would use SIMIT CTE, as mentioned before, for doing much more complex things, like these blocks that I showed you, that actually run, an entire program code, evaluate the different signals. And again, this is, the most complex thing it can do. All the other stuff, like the tank valves and so on, they are made with CTE as well. And as I said, in CTE, you could even import your FMUs, functional mock-up units from other simulation packages, these simulation packages like AIMSIM, if you know AIMSIM, or MATLAB with Simulink. So they can produce you FMUs that you could read in CTE and then import into SIMIT this way. So very, very powerful tool.
Okay, thank you.
Any further questions from anybody else? Okay, if that's the case, then I would, I'd like to thank everyone for their attendance. Thank you to Michael for his excellent presentation there. Just a reminder, of course, this was part 2 of 4 that we're running this week with our Digital Twin Week. I do hope you can join us tomorrow again, where we'll be looking at Mechatronics Concept Designer, and then on Thursday where the whole team will be back to show you digitalization in active with a complete thematic machine simulator offering and more available tools from CEOS. So thank you for your attendance. Enjoy the rest of your day and hopefully see you again soon. Thank you. Goodbye. Well done, Michael. Well done, buddy. Are you still there?
Yeah, I am sorry. I was just checking something.
I was impressed with what I saw.